Good morning. Okay, so we need to get going. Let's start in I guess 1 minute. Wait 1 minute. Let's start. Okay, so we're going to start now. We have a lot of material to cover today. But first we're going to go over homework 6, which was due today. So does anyone have any questions about homework 6? Do you mean 5.6 number 1, Michael? Okay. Okay, so which part? Well, let's start from the beginning. Okay, so um 5.6 number 1 says the cumulative distribution function for the continuous random variable x is the following. I asked you to find these things. So let me copy it. No, period. Doesn't seem to be copying. Okay. So this is homework 6 solutions. This is 5.6 number 1. Okay, so number 1, we have this. Oh, okay, right. So this is 5.6 number 1, 0 for that, and x equal 3, it's equal to that. So here we are. The formatting. Actually, maybe if I do this. Let me just check something. 1 minus k over x squared. Okay, so that's the piecewise function. Okay, so find the value of k. So this is the cumulative distribution function. And so if you integrate this from -infinity to infinity, no, okay, so solution. Okay, so number 1, part A, when x is 3, Okay, so here's the thing. So capital F of x is 0 for x less than 3, right? So that means that the PDF little f of x is also 0 for x equals 3, right? So note that little f of x is equal to 0 for x less than 3, right? Because of how what capital F of x is telling you, the cumulative distribution function. Now the now little f of x is also going to be 0 at x equals 3. Okay, because little f of x is continuous, and so if it's always 0 for x less than 3, it has to be 0 again. How do I put this? Let me put this way. Capital F of x, capital F of 3 is going to equal 0. And that's because the cumulative distribution is 0 up to 3, and then it has to stay 0 at x equals 3. And so capital F of 3 is equal to 0, but that's equal to 1 minus k, little k, over x squared, which is 3 squared. Okay, and so that means you can solve for k. So solve for k and get that k is equal to, so then you get k over 9 is equal to 1, so k is going to equal 9 to get k equals 9. Okay, does that make sense? So k equals 9 in A. Okay, because capital F of 3 is equal to 0. Okay. For B, it says sketch the graph of capital F of x. So now that we know that k is 9, we just want to graph this. So it's 1 minus 9 over x squared. So here's x equals 3. And here are the x values. These are the y values. This is x equals 3. And so it goes through the other. Okay, and so then 1 minus 9 over x squared. So so as x approaches infinity, 1 minus 9 over x squared for x greater than 3, greater than or equal to 3. Let me just check. X greater than or equal to 3. Okay, so for x greater than or equal to 3, it's 1 minus 9 over x squared. So when x equals 3, you get 0. As x goes to infinity, it's converging to 1. So you have a horizontal asymptote at y equals 1. So it's going to start at here, and it's going to just go to the right like this. And it's going to be 0 everywhere to the left. So I'm going to use this pink here to graph it. Let's see, you get this curve here. You get this curve here. And it goes to the left because it's 0 for x less than or equal to 3. This is y equals capital F of x. Okay, so does that make sense? Okay, so then that is the graph of y equals capital F of x. Okay, so the graph is on the whiteboard. And then C, find the probability that x will take in a value less than 4, between 4 and 5, greater than 6, less than 2. So let's do one of them. Let's find the probability that x is less than 4. So this is equal to the integral. Actually, this is equal to the probability, since x is a continuous random variable, you can include 4. It doesn't change value, and that's equal to capital F of 4. And so capital F of 4 is 1 minus 9 over 4 squared. And so that's equal to 1 minus 9 over 16. That's equal to 7 over 16. Okay, and so that's one of the probabilities, and you can find the other ones kind of similarly. And D, find a probability density function of X, right? This is not unique. And so one way is take the derivative of capital F prime of X. And so then that's the derivative of, that's d dx of 1 minus 9 over x squared. And so that's equal to d dx of 1 minus 9x to the negative 2. And so then that's equal to 18x to the negative 3, which is the same as 18 divided by x cubed. Okay, and so that's for x greater or equal to 3. For x greater or equal to 3, and then 0 elsewhere. Okay, so to write that out nicer, little f of x equals equals 18 over x cubed. And this is for x greater or equal to 3 and 0 elsewhere. Okay, and so that's the E, sketch the graph of the probability density function. So for E, it's on the whiteboard. 18 over x cubed. You have 18 over x cubed. For x greater or equal to 3. I'm writing that on the side so I don't forget. So you have x greater or equal to 3. And so when x is equal to 3, you have the height of 18 over 3 cubed, which is 18 over 27, which is 2/3. And then it looks like this. And then it's 0 elsewhere. So then it'll look like, let me use another color so it stands out. And then it's 0 everywhere else. Okay, so this is y equals little f of x. Okay, so then that's the sketching the graph. Okay, and so that's that problem. Okay, so now we need to keep going with the material. Okay, so that was homework 6. So today we're going to talk about chapter 6, which is on the mathematical expectation of a random variable. Okay, This class is going to have to be a little bit longer than other classes, so I cover enough material. So 6.1 is on the mathematical expectation of a random variable. Okay, and so 6.1.1 is an introduction. And so the most important number associated with a random variable is the expected value. Okay, and so this is very important to learn in probability theory. And so the next section is on the mathematical expectation of E of X. So we'll start with the definition. Definition 6.1. The mathematical expectation of a discrete random variable, Epilex, with probability function from f of x is the quantity capital E of x, which is equal to the sum which is equal to the sum over x of x f of x, provided that the sum over x of absolute value of x f of x is finite. So the series converges absolutely. The sum over x notation. That notation, ignore the box, denotes summation over all values little x that are possible values of the random variable capital X. Okay, so we're only summing over all possible values little x of the random variable capital X. And note that E of x is also denoted by okay. So example 6.1 illustrates this. So example 6.1, let capital X be the numerical value, numerical outcome of one roll of a die. Find E of X. Okay, so solution, the possible values of capital X, well, they're the numerical outcomes of one roll of a die, so the possible values of X are 1, 2, 3, 4, 5, or 6, because those are the possible values of one roll of a die. So the probability function of capital X is little f of x, which is equal to 1/6 for x equal to 1, 2, 3, 4, 5, or 6, right? The probability that capital X takes on a value of any of those values is 1/6. So we have little f of x. And so we have E of x in terms of little f of x. That's why we needed capital F of x. That means that the mathematical expectation of capital X is capital E of x, which is equal to the sum over all possible values little x overall possible values of capital X, namely little x of x times f of x. And so that's equal to, so the first possible value of x is 1. And so it's times f of 1 times f of 1. I guess I'll write this out. Plus 2 times f of 2 plus 3 times f of 3. I wouldn't normally use brackets. I'm using brackets here to emphasize the multiplication, so to help you visualize where the sum's coming from. But you wouldn't. I guess brackets might be a weird thing to use. But I think it better illustrates, just to make sure you see the multiplication going on, right? Okay, so we're taking all the possible values of capital X called little x, which are 1, 2, 3, 4, 5, or 6, and we're multiplying them correspondingly by the probability that capital X takes on those values. So 1 times f1 plus 2 times f2 plus 3 times f3 plus 4 times f4 plus 5 times f5 plus 6 times f6. And so we've now taken the sum of all possible values of capital X, called little x. And so that's equal to now 1 times the probability of 1, f of 1 is 1/6, right? And this is plus 2 times f of 2, which is also 1/6, plus 3 times f of 3, which is also 1/6, plus 4 times f of 4, which is also 1/6, plus 5 times f of 5, which is 1/6, plus 6 times f of 6, which is 1/6. And so now you have the sum of products of this form. This is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 times the distributed 1/6. Right? And so then that's equal to, well, the sum from numbers from 1 to 6 is 21. Okay. And so 21 times 1/6, and so that's equal to 21/6. And in simplest form, that's 7/2. And 7/2 is decimal is 3.5. So you expect the mathematical expression of capital X in that example, in example 6.1, is 3.5. Okay, this is provided that the sum over X. Note that the sum this sum is finite, since the sum over X of absolute value of X times f of X is equal to the sum where this is just X, and that's since all the possible values little x of capital X are positive, right? Little x is only being considered as 1, 2, 3, 4, 5, or 6. And so when you take the absolute value of each of them, it's still x. And so by finding that e of x, finding that this expression was 3.5, which is finite, this also means that this is finite. And so we can then say from this definition that e of x is equal to this, because when we calculate this, we got 3.5, which means this is finite, which means then we can say this equals that. Okay, does that make sense? Okay, so that's that example. Okay, so next is example 6.2. So let capital X be a discrete random variable with probability function f of x, which equals which is equal to 1/3 for x equals 3, 2/3 for x equals 9. Okay, and so the problem is find E of X. Okay, and so the solution, well, E of X. So we're going to take the sum over all values, possible values, little x or capital X of x times f of x. So we have that's equal to 3 times f of 3 plus 9 times f of 9. So that's 3 times f of 3, which is 1/3, plus 9 times f of 9, which is 2/3. So that's equal to 1 plus 6, which is 7. Okay, and it's right, since all the possible values, little x of capital X are positive, the absolute value of x, right, is the same as x. And so we were actually proving that we're still saying that this is finite because this sum is the same as this sum. And so by showing this is 7, this is finite, which means by the definition, E of X is equal to 7. Okay, I skipped the step where I use that. Okay, because it's obvious. Okay, so definition 6.2. The mathematical expectation of a continuous random variable capital X with probability density function little f of x is the quantity. So keep in mind this is a continuous random variable x now. Okay, so we now have a continuous random variable x, and so I italicized it, which is a little. It doesn't, see that, but I'm emphasizing that. So it's this quantity, and it's different because this is a continuous random variable as opposed to a discrete one. I have to plug in my charger now at this point. Okay. Okay, good. Okay. So E of X is equal to the integral from negative infinity to infinity of x f of x. Dx, provided the integral exists. Okay. And so this is the mathematical notation of a continuous random variable x with probability density function f of x. And so that's how you calculate the mathematical expectation for a continuous random variable. This is example 6.3. Let capital X be a continuous random variable with probability density function f of x. Which is equal to e1x squared. This is for 0 less than x less than 1/3 and 0 elsewhere. Find E of X. E of X is equal to, now this integral, provided the integral exists. The integral exists means that you get a finite value. Okay, and so now this is equal to, so it's little f is 0 except in this interval, and so you only need to integrate from 0 to 1/3. Okay, and then it's x times f of x, which I'm going to put in brackets, which is 81 x squared. That's a little f of x dx. And so you just need to integrate that. So this is the definite integral from 0 to 1/3 of 81x cubed dx. Okay, and so now this is equal to 81 times 1/4 x to the 4th. I'm going to move the 1/4 outside, so it's going to be 81 over 4 times x to the 4th. It's going to be evaluated from 0 to 1/3. Okay. And so this is 81 over 4 brackets. And so this is 1/3 to the 4th power minus 0 to the 4th power. And so then that's equal to 81 divided by, and you have 4 already there. And then you have 3 to the 4th, which is 81. 81's cancel, and you get 1/4, which is 0.25. Which is 0.25. Okay, and so that's the mathematical expectation for that continuous random variable. Okay, so there's an example of calculating the E of x for a discrete random variable, and this one for a continuous random variable. This is 6.1.3. Y E of x. Y E of x is called the mean of capital X. Okay, so to illustrate that, there's this example 6.5. A class of capital N students is given a test. The possible grades are A, B, C, D, and F, with numerical values 4, 3, 2, 1, and 0, respectively. Suppose we choose a student at random, okay, from the class, and let capital X be the numerical grade obtained by the student. What is X? Okay, so we're not actually given values. So you might ask yourself, how do you get this? So we're going to look at a general answer to this question. So let n sub x, we introduce terminology, let n sub x equal the number of students with grade X. No, we don't take the antiderivative twice. There's an x here, right? We multiply by x first because the integral is x times f of x. Okay, yes. So we only integrate once. Okay, the multiplication was the times x, and then we integrated once to get the x to the 4th over 4. You're welcome. Okay, good question. So here, back to this example. So everyone come back to this example. Let n sub x equal number of students with grade x. Okay, then f of x is equal to sum over x of x f of x, which is equal to the sum over x of x times n sub x over n. And so that's equal to, now, okay, so the probability of f of x, right, is the number of students who get the grade of x divided by the total number of students. So that's n sub x over n. And so then just the over n you can distribute. And so you can think of this as one fraction as the sum over x of x times n sub x divided by capital N. And so now f of x is equal to that. What that's equal to is that this thing, the sum over x of x times n of x, n sub x, that's taking each grade and multiplying it by the number of students who got that grade, and then adding those products. Well, the numerator of that fraction is the sum of grades by students in the class. That's this thing. This sum in the numerator is the sum of grades by students in the class, and the denominator is the number of students in the class. Okay, if you take the sum of the grades and divide by the number of students, that's equal to the average grade. So you can see that in this example, sorry, this was E of x. E of x, the expected value, is the sum over x of x times f of x, which is equal to this times this, which is the probability function. You can distribute the 1 over n. That numerator is the sum of the grades by students in the class, and the denominator is the number of students in the class, and so that equals the average grade. So E of x here is the average grade of students in the class, okay? Even though I didn't give any of the values, this is a proof that proves. So the above proves that E of x is the average grade of students in the class. As you see in this example, how E of x is the average. Okay. Okay, and note another way to say that in this example is that the mean of x is the average of the values weighted by their frequencies. The weighted by the frequencies means you're weighting each grade by how many students who got that grade. So this is example 6.6. Show if capital X is the number selected at random from a finite set, capital A, of numbers, then capital E of X is the mean of the set, capital A of numbers. Okay, so this is very similar to the other example. Okay, so we're going to suppose that capital A is equal to a set A1, A2, A3, AN, such that A sub I is a number for 1 less equal to I less equal to N. Okay, is a number. Okay, so each of the AIs are numbers. Okay, not necessarily distinct. Okay. F of X sub I is equal to the probability that capital X is equal to a sub I. It's the probability that you choose a particular value, but that's equal to the number of values in the set, which are equal to that number a sub I divided by the total numbers in the set, which is n. And so this is for I equals 1, 2, 3, up to including little n, and where k sub I equals the number of elements in capital A equal to a sub I. Okay, so the probability that capital X has this value, one of these values, is the number of times that value appears in the set, which is k sub I, divided by n, little n, which is the number of objects we have in this A. Okay, so therefore, E of X is equal to the sum from I equals 1 to m of x sub I times f of x sub I. Okay. Oh, wait, sorry. This is for I equals 1 to m. Okay. Also, where we make the first little m elements in capital A distinct, and then the remaining n minus m elements are repeats of the first little m. Okay, so we just arrange these elements so that the first little m of them are distinct, and then the rest of them are the ones that are repeated from the first little m. Okay, so we look at the I values from 1 to m, which are distinct values of a sub I in the set, and say the probability of x attaining one of those first little m distinct values is the number of times that value is repeated in the entire set divided by the total number of elements in the set. Okay, so therefore the expected value is the sum from I equals 1 to little m of x sub I times f of x sub I, right? Because the only values that are distinct are from I equals 1 to little m. And so then that's equal to the sum from I equals 1 to m of x sub I times f of x sub I. F of x sub I is k sub I over n for all those values from 1 to m. We're only continuing to sum there because the rest are repeated, and that's considered in the sum. And so then that's equal to the sum from I equals 1 to m of x sub I times k sub I, and then the n in the denominator distributes, and so you can just think of it as the denominator there. But now that numerator, the sum from I equals 1 to m of x sub I, k sub I, that's summing over all the distinct values of x sub I and then multiplying them by the number of times they appear and then adding those products. That's the sum of all the a values. That's a1 plus a2 plus a3 plus dot 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 plus a sub n, all of them, divided by n. And so if you do that, that's equal to the mean of the set capital A of numbers. Okay. So E of X is equal to the mean of the set A of numbers. And so we proved that E of X is the mean of the set A of numbers. Okay. So that example is done. Okay, so next is 6.1.4, which is on the strong law of large numbers and why E of X is called the mathematical expectation of Epilex. Okay, so we start with theorem 6.1, which is the strong law of large numbers. Let capital S be an experiment. With sample space, capital S. Let capital X be a random variable defined on capital S with E of X equaling to mu. If S is repeated little n times under identical conditions, and X sub I is the random variable capital X on is the value of the random variable capital X on the ith performance of capital S, then the probability of the limit as n approaches infinity of the average of those values, x1 plus x2 plus dot 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 plus x sub n over n is equal to mu. It's equal to 1. Okay, so the probability that the average of those n values is mu. I mean, the probability of the average, the limit of the average equals mu is 1. Or we expect I should really say and. I'm going to say and we expect the average of many observed values of capital X to be approximately equal to E of X. Okay, so if the probability of the limit of the average is mu is 1, then that means that what should happen is that for sufficiently large n, for really large n, this average should be very close to mu, because the point is that the average is approaching mu. The probability the average approaches mu is 1. And so approaching mu means that as little n gets larger and larger, the average is getting closer and closer to mu. That's a limit has a more precise and rigorous meaning, but usually when you teach it, you say that because it's a little complicated and it's hard to understand. So I'm using this loose idea of what limit means, right? So, but basically, the average is getting closer and closer to mu as little n is getting larger and larger. And so, since that's what this equation says, the probability that is 1, then what should happen is that the average should be approximately equal to mu, which is E of X for large little n. Little n is the number of times the experiment happens. It's repeated n times under identical conditions, right? Okay, so this experiment S is repeated n times. So n is the number of times you repeat the experiment. The sum of x1 to xn in the numerator, right? This sum is the sum of all the values of your experiment for those n times. And you're dividing that sum by n. So you're getting the average value of those n experiments. And so it's saying, right, as the number of times you repeat the experiment gets larger and larger, the average you find from those n times is approaching the average, the E of x. Okay. That's the strong law of large numbers. Example 6.7. Suppose capital X is the length of life in years of a certain type of battery. Then little f of x is equal to three-fourths times 2x minus x squared, or 0 less than x less than 2, and 0 elsewhere. Okay. Okay. Part A, show that the expected value of this x is 1. Okay. Solution. Let's calculate E of x. E of x is equal to, so here x is a continuous random variable. And so we integrate. But if we integrate from negative infinity to infinity, we only need to integrate from 0 to 2 because little f is 0 everywhere else. And so that means f of x times f of x would be 0 everywhere else. And so you don't have to integrate there. So it's only from 0 to 2 of that little x times f of x, which is that expression, right? And so just like the other example earlier, you're multiplying by x. And so now this 3/4 can be moved outside the integral. And then you have the definite integral from 0 to 2. And then x times 2x minus x squared is 2x squared minus x cubed, dx. And so then that's equal to an antiderivative of 2x squared minus x cubed, which is 2/3 x cubed minus 1/4 x to the 4th. But it's evaluated from 0 to 2. And so then that's equal to, so now it's 3/4 times, what's in the bracket? What's in the bracket is that expression when x equals 2 minus that expression when x equals 0. So when x equals 2, you have 2/3 times 2 cubed minus 1/4 times 2 to the 4th. And then when x is 0, you have 2/3 times 0 cubed minus 1/4 times 0 to the 4th. Okay. Okay, and so then that's equal to 3/4 times, and now it's one expression minus the other expression. The first expression, 2/3 times 2 cubed, that's 2/3 times 8, that's 16/3, minus 1/4 times 2 to the 4th. 2 to the 4th is 16, 1/4 times 16 is 4. So it's that. And then the other thing is just 0 minus 0. So this is 0. And so now this is equal to, this is equal to 3/4 times 16/3 minus 4 minus 0. So 16/3 minus 4 is the same as 16/3 minus 4, which is 12/3. So this is equal to 3/4 times, well, 16/3 minus 12/3 is now 4/3. So it's 3/4 times 4/3, which is equal to 1. And so E of x is equal to 1. And we're done. Show that E of x equals 1. That's what we did there. B. If we bought 2,000 batteries, we can expect the average length of life to be 1 year by the strong law of large numbers. Okay, I'm just telling you something of me. So, right, the strong law of large numbers tells you that the probability that the average is the expected value is about 1 for really large n. And so each battery has a certain length in life, right? Each battery lasts a certain amount of time, right? So each battery can be thought of as an experiment, and where the value of x is how long that battery lasts. Okay, and so you repeat this experiment under identical conditions. You have 2,000 batteries, and you find out how long each of the 2,000 batteries lives for, and I guess you do the same things with batteries. So then, since 2,000 we're saying is a large enough n, we're saying that we should expect that the average life of those 2,000 batteries is going to be the expected value, which is 1. And so so the average we're going to assume is 1. The average life of those batteries is 1 year. Okay. So what this is saying, it should be close to 1. It should be close to mu. Here, the 1 is the value of mu, not the 1 here. The 1 here is for the probability. In this example, the 1 is the value of mu. So the strong law of large numbers does not say the average equals the expected value. It says for really, really large number of repeated experiments, for a really, really large number of n, the average should be close, will probably be, almost certainly be really close to 1 probability that the average will be close to mu. Okay. So that's 6.1. 6.2, applications. Okay, so let's look at what's called a fair game. So 6.2.1 is on fair games. Okay. So definition: a fair game is one in which the expected net gain of each player is 0. Okay, the net gain is the expected value. Okay, so example 6.8, we're going to use that idea. So in the game Chuck-a-Luck, a player pays $1 and chooses one of the numbers 1 through 6. 3 dice are then rolled, and if the number he or she chooses appears 1, 2, or 3 times, the player receives $2, $3, or $4 respectively. Is this a fair game? If not, what should the fee be to make this a fair game? Okay, so in the game Chuck-a-Luck, a player pays $1 and chooses one of the numbers from 1 through 6. 3 dice are then rolled, and if the number he or she chooses appears 1, 2, or 3 times, the player receives $2, $3, or $4 respectively. Is this a fair game? If not, what should the fee be to make this a fair game? Okay, so again, a fair game, by this definition, we defined a fair game to be one in which the expected net gain, the expected value of each player is 0. Expected net gain means expected value. Of each player is 0. Okay. So the question is asking, right? So the question is asking whether or not the expected value is 0. Okay. So let capital X be the net gain of the player in units of $1. Okay. The expected value of little x defined below is $1, is 0. It's asked whether the expected value of x defined below is 0. So let x be the net gain of the player in units of $1. If the fee is $1, possible values of capital X are. So the possible values of X, well, if you're paying $1 to play the game, and the amounts you can win are 2, 3, or 4, or you could win nothing, then the net gains, the possible values of net gain are going to be -1, 1, 2, or 3. If you don't win $2, $3, or $4 and you paid $1 to play the game, your net gain is -1. You've lost $1, right? You've lost 1 unit, $1. If you win $2 and you paid $1 to play, your net gain is $1. If you won $3 and you paid $1 to play, you have a net gain of $2. If you win $4 and you paid $1 to play a game, your net gain is 3. So the only possible net gains you can have are -1, 1, 2, or 3 in this game. Okay, so those are the possible values of capital X, the net gain of the player playing the game. Okay, to find the probability function of capital X, consider each roll of a die as a Bernoulli trial, and the appearance of the number chosen as a success in that trial, and the probability of success in each Bernoulli trial / roll of a die is 1/6. Right? There's 1/6 chance that the number you chose each time you roll a die is the number you chose. And the probability of capital X and the probability of and the probabilities of capital X are, well, the probability that X equals -1, that your net gain is -1, is equal to the value of the binomial probability function of 0, 3, 1, 6. 0, 3, 1, 6. What does that mean, right? Remember, we have Bernoulli trials. We roll the die 3 times, right? Each roll of a die is a Bernoulli trial. So that we perform 3 Bernoulli trials. In order to have a net gain of -$1, that means that the number you chose, right? If I chose number 4 and I rolled the 3 die, that would mean that the number 4 did not appear in any of the 3 die, right? And so that means I paid $1 for the game, and the number I chose appeared 0 times, so I made 0 money. And so I have a net gain of -1. I have a net gain of -1 if you never win, right? You roll the die 3 times, and the number you chose never appears, okay? The number appearing in a roll of a die is a success in a Bernoulli trial. So you have 3 Bernoulli trials. The number appears 0 times, so you have 0 successes. Success in each Bernoulli trial has probability 1/6. there's a 1/6 chance the number you chose appears when you roll the die. There's 6 possibilities, each with equally likely outcomes, 1, 2, 3, 4, 5, or 6. You've chosen one of those numbers, there's a 1/6 chance that you succeed in getting that number when you roll the die each time. Okay? Okay, so that's B of 0, 3, 1, 6. 3 Bernoulli trials, 0 successes, 1/6 probability of success in each Bernoulli trial. And so that's the same as, so the value of that expression, you're not just calculating the value of a binomial probability function. That's 3 choose 0 times 1/6, the probability of success, raised to the 0th power because you succeed 0 times, 5, 6, the probability of failure, raised to the 3rd power because you fail 3 times. And when you multiply all this out, you get 5 cubed divided by 6 cubed. And so that's equal to 125. 125 divided by 6 cubed, which is 216. Okay, so the probability that x equals -1, that your net gain is -1, is 125 over 216. The probability that now the other possible value of x is 1. So the probability that x equals 1 is equal to b of 1 colon 3 comma 1 6. So now you have 3 Bernoulli trials and you have 1 success in 3 Bernoulli trials where the probability of success is 1/6, right? A net gain of 1 means you succeed once in getting the number you chose. So you roll the die 3 times, and if you have a net gain of 1, that means you won. That means the number appeared once. So you got $2. You paid 1 for the game. You have a net gain of 1. Okay, so the number appears once. And so if you roll the die 3 times, that means you succeeded once in 1 Bernoulli trial of getting the number you chose, and you failed the other 2 times. Okay, so 3 Bernoulli trials, 1 success in those 3, and probability of success is 1/6. Okay, and so that's equal to 3 choose 1 times 1/6 to the first power times 5/6 to this second power. And so when you multiply that, 3 choose 1 is 3. And then you have the fraction 5 squared, which is 25, divided by 6 cubed, which is 216. And so then that's equal to 75 divided by 216. So that's the probability x equals 1. Next one is the probability that x equals 2. And so we're just going to follow this pattern, right? 2 successes in 3 Bernoulli trials, probability of success is 1/6. Okay, and that's equal to 3 choose 2 times 1/6 to the second power times 1/6 times 5/6 to the first power. And so 3 choose 2 is 3 times 1/6 squared times 5/6 to the first. So you get a fraction 5 over 216 here. And so then that's equal to 15 divided by 216. And the last one is the probability that x equals 3. Your net gain is 3 by winning $4, paying 1 to play the game. So all 3 numbers appear. So you have 3 successes in 3 Bernoulli trials where the probability of success is 1/6. And that's equal to 3 choose 3 of 1/6 to the third power times 5/6 and probability of failure raised to the 0th power. Number appears all 3 times, so you have 3 successes, 0 failures. 3 choose 3 is 1, 1/6 cubed, 5/6 and 0 is 1. 1/6 cubed is 1 over 216. So that is 1 over 216. So those are the probabilities of all possible x values. And so that means that the expected value of x, e of x, is equal to, well, you take each possible value of x and multiply them correspondingly by the probability of x being that value. So -1 times 125 over 216 plus 1 times the probability x equals 1, which is 75 over 216, plus 2 times the probability that x equals 2, which is 15 divided by 216, plus the last possible value of x, which is 3, times the probability x equals 3, which is 1 divided by 216. Okay, until you add up those products and you get negative 17 divided by 216, which is equal to, as a decimal, negative 0.0787. So the game is not a fair game. Okay, on average, if a player plays the game many times, you should expect that on average, he or she will lose about 8 cents per game. And that's because 0.0787 is about 8 cents rounded up. Okay, so right, 1/100th of a dollar is a cent, and so this 7 here in the hundredths place is like 7 cents, but then it's 87 hundredths of another cent, which rounds up to 8 and another cent. So this is really close to 8 cents rounded up. Okay, so the game is not fair. It looks like you might actually be in your favor with these rules, but then when you do the expected value, it turns out that the player is at a disadvantage, which is what most games are usually like. Kishan, you have a question? Yeah, what is it?
I have a question. So how do you get the values of the capital X?
Okay, because when you play the game, right, what are the possible amounts you can win?
Okay,
What are the possible amounts of money you can win in the game?
like $2, $3, or $4.
Right. And so how much did you pay to play the game?
The player pays $1. Okay.
Right. And so, well, so that's the amount you can make, right? If you don't make any, right? If you don't make any money, how much you made 0, right? So if you pay $1, then what's the net gain?
-1.
-1, because you paid $1 to play the game, but you didn't make anything, right? So your net gain is negative $1.
Oh, okay.
Does that make sense?
Yeah.
Like if you owed me $1, instead of saying, you could say you have negative $1. Does that make sense?
Okay.
The negative means opposite. So $1 would mean you have $1, and so -1 would be like owing $1. Okay.
Okay.
So playing the game, paying $1 to play the game, and then making 0 means you have a net gain of -1. It's in the opposite direction. Okay, but if you made $2, what's your net gain?
1.
1, right? If you made $3, what's your net gain?
2
And if you made $4, what's your net gain?
is 3.
So what are the possible net gains that you could have for playing the game?
-1, 1, 2, or 3.
Good. Those are the possible net gains of the game. So if you assign capital X the value of your net gain, the possible values of capital X are
Okay.
what?
But capital X.
What are the possible values of capital X?
-1, 1, 2, or 3.
Does that make sense?
Yeah.
Okay, there you go. That answers your question, right?
Yeah.
Okay, good. Okay, so those are the possible values of capital X. You find the probability of X having each of those possible values. That gives you the probability function of capital X. You use the probability function of capital X to get the expected value of capital X. Okay, which is the sum over all possible values of x times f of x. Okay, the game is not fair because we got the expected value of the game is not 0. So that's part A. Part A was, so is this a fair game? So the answer was no. If not, what should the fee be to make this a fair game? And so that's what we're going to answer now. We're going to find out the fee that we should make the game, change the fee to make it a fair game. Okay, so let K denote the fee. So instead of the fee being $1, we're changing it to K dollars. So let K denote the fee. The goal now is to find the value of K, which will make the game fair by making the value of the expected, by making the expected value 0. Okay, so we are going to compute the expected value using the fee as the variable K. Setting the expected value to 0, we get an equation with one variable K. Solve for K, and that is the value of the fee that makes the expected value 0 and the game fair. That makes sense? Okay, and so we're going to compute the expected value using the fee as the variable K. Instead of assigning a value to the fee of the game, we're going to just make it a variable K. Setting the expected value to 0, we get an equation with one variable K. An equation that says the expected value 0 is equal to what its value is using the fee as K. And you solve for K, and then that's the fee that makes the game fair. Okay. Thus, if E of X is 0, then zero equals E of X. And E of X is equal to, well, it's the sum over all possible values of X, right? Note that originally, when the fee was $1, the possible values of capital X, the possible net gains of the game, the possible values of X were -1, 1, 2, or 3, right? That's if you paid $1, right? Possible values were that because the possible wins were 0 if you didn't make anything, 2, 3, or 4. So you subtracted 1 from each of the possible amounts you could win. You could win 2, 3, 4, and I included 0. So you would subtract 1 from each of them for the fee, and the net gains would be -1, 1, 2, or 3. Now, the fee is K dollars. So the possible values of capital X are, which the possible net gains, are now, well, the possible wins are still 0, 2, 3, or 4, but the amount you paid is now variable K. So you're going to subtract K from each of those win totals. So the possible values of X are 0 minus K, comma 2 minus K, comma 3 minus K, comma 4 minus K, right? It's all the values, all the possible amounts you could make, which are 0, 2, 3, or 4, and subtracting the fee from each of them, which is K. 0 minus K is K, but I wrote 0 minus K to just illustrate how you get minus K. Okay, so these are the possible values of capital X, right? But now correspondingly, right, the probability that X equals 0 minus K, which is the same as probably X equals K, is equal to what it was for -1. because it's still 0 successes and 3 Bernoulli trials with a probability of success of 1/6. All we did was change the amount you pay for the game. We didn't change the probabilities of rolling a certain number of times. So the probability that you make negative k instead of -1 is 125 over 216. So we still have this probability. The probability that x is equal to 2 minus k, well, that corresponds with the probability that x equals 1 when the phi was 1. So that's going to be 75 over 216. The probability that x equals 3 minus k corresponds with the probability had with the other phi, which was when the phi was 1, probably x equals 2, which is 15 over 216. And last, the probability that x is equal to 4 minus k corresponds with the probability that x was equal to 3 earlier, which was 1 over 216. So we have we still have these corresponding probabilities for each of the possible values of x. All that changed was the amounts that you, the net gains. Okay, and so then 0, this is all in the note here. Actually, instead of note, I'm going to call this side work. Okay, so E of x is now the sum over all possible values of x times their respective probabilities. So one possible net gain is 0 minus k, and the probability of that is 125 over 216, plus the next possible value of k, which is 2 of x, which is 2 minus k, times the probability that x is equal to 2 minus k, which is 75 divided by 216, plus another possible value of x, which is 3 minus k, times probably x equals 3 minus k, which is 15 divided by 216, plus the last possible value of capital X, which is 4 minus k, times its corresponding probability, which is 1 over 216. That's how you get that sum. Okay, and so when you expand and solve for k, expanding the expression on the right side of the equal sign, and then solving for k, we get that k is equal to 199 divided by 216. And that's approximately equal to 0.92 decimal. Okay, and so our conclusion is that if you make the fee for Chuck-a-Luck 92 cents, or $0.92, then the game is fair because the expected value is 0. Because the expected value of the net gain of each player is 0. Okay. Okay, so that's one example of another example. And so now we move on to the next section. So this is going to be section 6.2.2. This is on decision problems. And this is example 6.9. Okay. A newly formed company plans to send a number of employees each year to an annual one-day conference held in an out-of-town hotel. The hotel offers a bargain rate of $30 per day per person. If reservations are received 30 or more days in advance. However, there is a cancellation fee of $15 per person. The regular rate is $40 per day per person. The company cannot be certain 30 days in advance of the exact number of employees it will send. However, management feels if capital X is the number it will send, then capital X is a random variable with probability function f of x is equal to 1/4, or x equals 4, 5, 6, or 7. Should the company make advance reservations? If so, how many? Give the answer that will minimize costs in the long run. Okay, so it's certainly possible that the number of people who go is different than what the number you might expect or something. And then so it's possible that the best choice in the long run is not necessarily the best choice in the short term, right? Sometimes you look at averages over a long period of time, and in a very short, in one life instance, something weird happens, and then it turns out that the best decision with the amount of information you had turns out not to be the best, doesn't have the best outcome. But we're gonna try for the what should happen over a long period of time. Okay, so example 6.9. A newly formed company plans to send a number of employees each year to an annual one-day conference held in an out-of-town hotel. The hotel offers a bargain rate of $30 per day per person if reservations are received 30 or more days in advance. However, there's a cancellation fee of $15 per person. The regular rate is $40 per day per person. The company cannot be certain 30 days in advance of the exact number of employees it will send. However, management feels if X is the number it will send, then X is a random variable with probability function f of X equals 1/4, where X equals 4, 5, 6, or 7. So the probability that because they're not sure right, they're not sure how the number of employees will send, and so X, these are the possible number of employees they will send, and the probability is 1/4 for each of them. Okay, so there's a 1/4 chance they send 4, there's a 1/4 chance they send 5, there's a 1/4 chance they send 6, and there's a 1/4 chance they send 7. That adds up to 1. There's no other possible value of X. Should the company make advanced reservations? If so, how many? Right? If they make an advanced reservation, it costs $30 per day per person. Okay. If they make a reservation advance, if they have to cancel the reservation because a person doesn't show up, that's $15 per person. And if they don't make a reservation for someone and they need another room, and it costs $40. Okay, so if more people come than they buy for, they have to pay a larger rate. If they have, if they reserve more tickets than they need, they have to pay a fee, right? So they want to get as close to the number that will happen, that to the actual. So they want to estimate how many. Okay, so let's see. So we're going to introduce some random variables here. Let y sub I equal the cost in dollars if the company makes reservations for I people. Okay, so y sub I is the cost in dollars for the company if the company makes reservations for I people. Okay, the possible values of y sub 4 are, well, y sub 4 is the cost in dollars if the company makes reservations for 4 people. So if they make reservations for 4 people, right, then the question is how much will it cost the company, right? So there's different possible values depending on how many people actually show up, okay? So if they make reservations for 4 people and 4 attend, then they paid $30 for each of the 4 people. That's $120, right? So if they make reservations for 4 people and 4 attend, each costs $30 at the bargain rate. So they got it right exactly. And so the possible values of y sub 4 are 120 if 4 people attend. But then if they make y sub 4 means they make 4 reservations. 5 people could attend, right? The possible number of people who attend are 4, 5, 6, or 7. If 5 people attend and they only made reservations for 4, they paid $120 for those 4 with 4 reserved tickets. The 5th person, they have to pay the regular rate, which is another $40. So you add $40 to 120 and you get $160. And so they have to pay $160 if 5 people attend, right? This is if they make 4 reservations in advance. This is a possible value of y sub 4. If 6 people attend, that means they made 4 people got the bargain rate of $30 per day per person per day. So that's 4 times 30, which is still 120. There's now 2 people who have to pay the regular rate. They pay the regular rate for 40 each. That's 80 in addition to the 120. So that's $200 they have to pay if 6 people attend. Okay. The other possible amount is that 7 people attend. If 7 people attend, the 1 additional person has to pay the regular fees. That's another $40 in addition to the 200. And so that's $240 if 7 attend. Okay, so the possible values of y sub 4 are $120, $160, $200, and $240. Okay, and keep in mind the probability of each of those values is 1/4 because the probability of each of these number of people attending is 1/4, right? And note that the probability that y sub 4 takes on each of these 4 values is 1/4. Okay, so assuming that the company pays for 4 reservations in advance, they would either have to pay $120, $60, $200, or $240 in total in the end. And the probability of each of those values is 1/4. Okay, now the possible values of y sub 5, let's do it this way. The possible values of y sub 5 are, well, they make 5 reservations in advance, right? And so what I'm going to do is I'm going to maybe write the parentheses first. So either if 4 people attend, right? If 5 people attend, if 6 attend, if 7. Okay, so those are the possible people who attend. Now, y sub 5 is assuming they pay in advance for 5 people. So if only 4 people attend, that means 4 people got the bargain rate of 30 each, so they paid 120. Right? Okay, sorry. Y sub 5 means 5 remain in advance. So the bargain rate is $30 for each of them in advance. So 5 times 30 is 150. So they pay $150 for the ticket, but only 4 people attended. So that means they don't need one of the tickets they paid for. So they paid 150, but they have to cancel one of them and they have to pay the fee of $15. And so that means they get back the 30, but they have to pay 15. So you subtract 15, and you have $130 before people attend. $135 before people attend, right? Because the first 4 tickets were at the bargain rate of $30 each, so that's $120. But then they paid a 5th ticket, which the net was they paid $30 for it, they got back their money, and then they paid the cancellation fee of $15. So each ticket they don't use costs now $15. Okay, so it's $120 for the first 4, and additional $15 for the ticket they didn't use. That's $135. If 5 people attended, then they made 5 in advance. They bought 5 in advance, and that matches up perfectly. Each was 30. So they paid $150 if 5 people attend. So see that if 5 people attend now, paying an extra ticket in advance, they saved $10 because they would have had to pay $160. Now they paid $150. But if 4 people attended, they had to pay an extra $15 as opposed they have to pay $135 instead of $120. So see that these two, one is worse, one is better. Okay. Now if 6 people attend and they paid 5 in advance, and the first 5, and the 5 they bought is in the bargain rate 150. The 6th one is for the regular rate of 40. So there's another $40 in addition to that 190. And so that's 190 if 6 people attend. That's $10 less than 200. So this is better. This is also better. That's the only one that's worse. Now here, if 7 people attend, they have to pay the regular rate for that last person, which is 40. So 190 plus 40 is 230. And so this is $230 if 7 people attend. Okay, so now these 3 values are a little bit better, and the one value here is worse. Okay, and remember, note that the probability that y sub 5 takes on each of these 4 values is 1/4. Okay, the possible values of y sub 6 are. So the possible values of y sub 6 are, again, the possibilities that are if 4 people attend, if 5 attend, if 6 attend, if 7 attend. Okay, so if 4 people attend, they made 6 reservations in advance. 4 of them are for the bargain rate of 30 each, that's 120. The 2 left over are the cancellation fees, that's another 30. So that's $150 in total. Okay, so you make this calculation, you have $150 there. That's y sub 6. The next one is, well, 5 people attended, and so they have to pay another cancellation. Okay, so if 5 people attend, then that means that they paid the bargain rates for 5 of them. So that's 5 times 30 is 150. They paid a cancellation fee for 1, so that's $165. If 6 people attend, then they hit the mark perfectly. They bought 6 in advance, 6 attended, so 6 times 30 is 180. That's $180. And if 7 people attend, then they paid 6 in advance. They made 6 in advance, 6 times. That's still 180, but then they pay the regular rate for the last person, which is 40. So now it's $240. Another $220. Another 40 on top of that for that value. Okay, and the possible values of that y sub 6 takes is probably is 1/4 each of them. Probably that y sub 6. Probably that y sub 6 takes on each of these 4 values is 1/4. And then the last one is y sub 7. the possible values of y sub 7 are, right? So y sub 7 is the amount that they have to pay if they make 7 reservations in advance. And so again, the possibilities are if 4 people attend, if 5 attend, if 6 attend, and if 7 attend. Okay, and so if 4 people attend, then bargain rate for 4 of them, that's 120. The other 3, they have to pay cancellation fee. That's 15 times 3 is 45. 120 plus 45 is 165. So they have to pay $165 if 4 people attend. If 5 people attend, they have to pay an extra cancellation fee. So that's another $15 they have to spend. And so that's 180. 15 plus 165 is 180. If 6 people attend, they pay an extra cancellation fee. And so then that's 180 plus 15. That's 195. And wait, no, I'm sorry, they cancel 1 less. And so as opposed to paying the canceling fee of $15, they incur the cost of the entire person. Okay, so like if 5 people attend, I'm going to do it the forward direction. If 5 people attend, they pay 30 fees, that's 150. They pay 2 cancellation fees, that's 30, right? If 6 people attend, 6 times 30 is 180. They pay 1 cancellation fee, that's 195. And then if 7 people attend, they hit the mark perfectly. All 7 are at the bargain fee of 30, so that's 7 times 30 is $210. That's $210 if 7 and 10. Okay, so those are the, and note that the possible values that y sub 7 takes, each of them probably 1/4. Probably, note that the probability that y sub 7 takes on each of these 4 values is 1/4. Okay, so we now have the probabilities for all possible values of all 4 random variables, y4, y5, y6, and y7. And so now we want to find the expected values of each random variable, right? So each random variable is talking about how much they would have to pay, assuming they make a certain number of reservations in advance, right? So y sub 4 are the amounts that they have to pay if they make 4 reservations in advance. Y sub 5 is the amounts they have to pay if they make 5 reservations in advance. Y sub 6 are the amounts they have to pay if they make 6 in advance. Y sub 7 are the amounts they have to pay if they make 7 reservations in advance. And so find the expected value of each. Find the average amount that they would have to pay over all possible number of people who'd attend, 4, 5, 6, or 7. Find the averages for each of these 4, and then see which average is the lowest. The average that's the lowest is saying that in the long run, considering all possible ways that 4, 5, 6, or 7 could attend, it would be saying the lowest amount would be saying on average which of the number of reservations would cost them the least. Okay, so let's find the expected values of each random variable. So the expected value of y sub 4 is equal to, well, the expected value of y sub 4 is you take each possible value of y sub 4, which is 120 in dollars, times its probability of 1/4, plus the next possible value, which is 160 times 1/4, plus the next possible value, which is 200, times 1/4, and then plus the last possible value, which is 240 times 1/4. And you add up all those products, and you get 700 over 4. $720 over 4. And 720 over 4 is 180. Okay, so expected, so you'd expect that if you kept doing this, thousands, millions of times, this situation on average, you would expect that they would have to pay $108 if they made 4 reservations in advance. If this situation happened a really large number of times. The expected value of y sub 5 is now take each possible value of y sub 5 and multiply it by its corresponding probability. So the possible values of y sub 5 are 135 and multiply it by 1/4 its probability, plus the next possible value, which is 150. That's, I'm looking at this line here, plus the next possible value, which is 150 times its probability of 1/4, plus the next possible value, which is 190 times 1/4, plus the next possible value, which is 230 times 1/4. Okay, now, so add up those products, and what you get for expected value y sub 5 is, as a decimal, 176.25. The expected value of y sub 6, and note that the expected value of y sub 5 is 176.25, means if you repeat this situation millions of times, then you wouldn't have to be that many times, but just to exaggerate. If you repeat this situation millions of times, on average, if they made 5 reservations in advance, on average, they would have to pay $176.25 in total, or however many people that ended up showing up, whether 4, 5, 6, or 7. Okay, and now E of y sub 6 is equal to, take each possible value of y sub 6, which is now this row, So you have 150. You have 150 times 1/4 plus 165 times 1/4 plus 180 times 1/4 plus 220 times 1/4. And then this is equal to, as a decimal, 178.75. And so that's that one. Then E of y sub 7 is equal to, take each possible value y sub 7, it's these 4 possible values, and multiply them by their corresponding probabilities, which are each 1/4. Add those products, and you get E of y sub 7 there. And so this is equal to 165 times 1/4 plus 180 times 1/4 plus 195 times 1/4 plus 210 times 1/4. And so you get the sum of products here, and you take the sum of those products, and what you get is $187.50. Okay, and so now you compare each of these 4 expected values, and you see that the smallest one is 176.25. That's E of y sub 5. Okay, and so the conclusion is that since E of y sub 5 is the smallest expected value amongst our 4 random variables, the company should make advanced reservations for 5 people. Okay, y sub 5. So on average, if you were to do, if this happened a million times, on average, considering all the possible people who would actually show up, on average, they would have to pay the least if they made 5 reservations in advance. Okay, and they should definitely make at least 4 reservations, because if they made fewer, there's going to definitely be at least 4 people who attend. And so why not make 4 in advance, right? That's obvious, right? And you wouldn't make 8 reservations in advance, because at most 7 people would attend. And so if you made more than 7 reservations in advance, you would know you would have to cancel at least however many more than 7 you bought. And so it's obviously only worthwhile to make 4 to 7 advanced reservations in advance. And it would be worse to make fewer than 4 reservations or more than 7. The best number of reservations has to be between 4 and 7. And so we find that between 4 and 7 inclusive, the best number in the long run is 5. but it's possible that in one situation, it's possible that 7 people attended, or 3 people attended, or 6 people. So it's possible this happening once, that your best choice in the long run doesn't give you the best outcome in any one particular, iteration of this experiment, of this situation. Okay, and so that's the example. So class is going to extend a little bit longer because I need to cover more material this class. And so this is example 6.10. And so this is an inventory problem. Okay, in any one week, the number of requests for a magazine is a random variable Epilex with probability function f of x, which is equal to the following. So it's equal to 5/12 for x equals 3. It's equal to 4/12 x equals 4. X equals 4. 2/12 x equals 5. And 1/12 x equals 6. Okay, that's your probability function there. The magazine sells for $1, and the cost to the owner is 50 cents. How many magazines should he order from the publisher per week if he wishes to maximize his expected profit? So any one week, the number of requests for a magazine is, okay. In any one week, the number of requests for a magazine is a random variable capital X with probability function that. Right? Okay, the magazine sells for $1 and the cost of the owner is 50 cents. So whenever the owner gets a magazine to sell, it costs him 50 cents. And so he sells it for $1, right? How many magazines should he order from the publisher per week if he wishes to maximize his expected profit, right? His profit is how much he sells the magazine for minus, the cost of 50 cents, right? But if he doesn't sell a magazine, then he only paid $50 but never made the dollar back, right? Okay, so the possible number of requests, meaning the possible number he sells, right, is 3, 4, 5, or 6. So he'll sell 3, 4, 5, or 6 of a certain magazine. Okay, and these are the probabilities, right? So 5, 12, 4, 12, 2, 12, 1, 12. If you add them, 5 plus 4 plus 2 plus 1, that adds up to 12. So these probabilities add up to 12 over 12 for 1. Okay, so there's no other possible amounts of magazines that he can sell. Okay, so this is going to be similar to the other example. Let y sub I equal to the profit in dollars of the magazine owner if the owner buys I magazines. Okay, so in each case, he either buys 3, 4, 5, or 6 magazines in advance. Buying fewer than 3 magazines in advance doesn't make sense because he knows he'll have at least 3 people who will buy them. Buying more than 6 magazines in advance also doesn't make sense because he knows he'll only have at most 6 people to sell them to. So the only number of magazines he should buy in advance to sell are between 3 through 6 inclusive, 3, 4, 5, or 6 to maximize his profit. Okay, so we'll let y sub I equal the profit in dollars if the owner buys I magazines. So we have 4 random variables there. Y sub I is representing, for each I is representing a random variable. So we have for buys I magazines where I is going to equal 3, 4, 5, or 6. Okay. Okay, so on the whiteboard, I'm going to write down the different values of each y sub I in a table. Okay. Okay, so it's now going to be on this table. Okay, so let's look at this table. So okay, so here in the first row is horizontal. So here in the first row, we're going to look at possible values of X. X are the number of magazines that he sells. He's either going to sell 3, 4, 5, or 6 magazines. The random variables we're going to look at are y sub 3. He buys 3 in advance. He buys 3 to sell. Y sub 4, he buys 4 to sell. Y sub 5, he buys 5 to sell. And Y sub 6, he buys 6 to sell. And then we're also going to just have here the probability that capital X equals little a. Okay, and so the probability that there are 3 people who buy a magazine is 5/12, according to the probability function I gave you. And then the PDF I gave you is 4/12 if X equals 4. It's 2/12 if X equals 5, and it's 1/12 if X equals 6. So those are the probabilities that those are the number of people who will buy a magazine, that he can sell that many magazines, 3, 4, 5, or 6. Okay, so for Y sub 3, the value of Y sub 3, if 3 people buys, well, if he sells a magazine for $1, but he need to pay 50 cents to get the magazine to sell, his net gain is 50 cents for each magazine he gets and is able to sell, right? $1 minus 50 cents. So the net gain of 50 cents for each of the 3 he buys, and it's exactly 3. So it's $1.50, right? If he has 4 in advance, he gets 4 in advance, and all 4 sell. They each make 50 cents, and so that's $2 in total. 50 cents times 4, that's $2 in advance, right? If 5 are in advance, if he has 5 exactly to sell and all 5 sell, he makes a net gain of 50 cents each. That's 2 times 50 cents. That's $2.50. If he gets 6 magazines to sell and all 6 sell, he makes a net of $0.50 each. 6 of them, so that's $3. 6 $0.50 is 3 full dollars. So he makes $3. Okay, that's if the number he gets matches the number he's able to sell. If he gets 3 magazines, but there's 4 buyers, well, he sells all 3 of the ones he got, but he doesn't have another magazine. So demand is larger than the supply. So he just still makes $1.50. He just can't make an extra 50 cents because he doesn't capitalize on the extra person that's willing to buy the magazine. There's 5 people willing to sell the magazine, but he only buys 3. He still only makes $1.50, and there's 2 people who also want the magazine, but he's not able to sell them because he only got 3 of them. And the same thing for 6. The 6 people want to buy a magazine, but he only has 3. He sells all 3 of them, and he makes $1.50, 50 cents for each of the ones he sells. Okay. Similar thing here. He made $2 by selling all 4 of the magazines he got, but there's 5 buyers. He can only sell 4 of them, and he still makes $2. And then if there's 6 buyers, but he only bought 4 of these magazines, he made $2 on the 4 he sold, and then he can't make any more from the 2 additional people who want to buy it because he only has 4 magazines. And here, if he buys 5 in advance, he sells, and there's 6 people who want it, he can only sell 5 of them. He makes $2.50, and then the 6th person can't also buy it, so he fails to make another 50 cents from that 6th person. Okay, that's if the amount who want to buy the magazine are more than the number he buys. But let's say he buys 4 magazines and only 3 people, he's only able to sell to 3 people. He makes 50 cents for each of the 3 people he sells it to. That's $1.50. But there's a 4th magazine that he bought $1 for but never sold, so he lost $1 there. So he made $1.50 on the 3 people he sold it to. And then he lost $1 for the first one. So he only makes 50 cents. So he's punished a lot for this one magazine he doesn't sell. So he only makes a net of 50 cents in this situation. He makes $2 in these 3. He only makes 50 cents there. If he buys for 5 in advance, right? And only 3 people buy, he makes 50 cents for the 3 he sells. That's $1.50. Then $2 he loses for the 2 he didn't sell. So it's $1.50 minus $2. He loses 50. Y sub 4. Wait a minute. Y sub 4. He buys 4 magazines. And he sells 3 of them. Oh, sorry, they're 50 cents each. So they're 50 cents each. So for the 3 that he bought, he makes 50 cents each. That's $1.50. For the 4th one, he paid 50 cents for the magazine. So it's $1.50 minus 50 cents. He gets a net gain of $1. He's not punished as that much. Okay, so he loses 50 cents for each one that he doesn't sell. So he sells 3 of the 5 here. So he makes $1.50. He's punished 50 cents for each of the 2 he doesn't sell. That's $1.50 minus $1. He makes 50 cents in total. He still has a net gain. Okay, if there's 4 people that sell it, 4 of them, he makes 50 cents each. That's $2. He's punished for 1 that he doesn't sell. $2 minus 50 cents is $1.50. This sounds $1.50 there. Good. And then if he buys 6 in advance, but only 3 sell, then he makes $1.50 for the 3 he sells. He loses 50 cents for each of the 3 he doesn't sell. He loses $1.50. So he makes $1.50, loses $1.50. He makes $0 in net gain here. Now, if he has 6 in advance and he sells 4 of them, that's $2, and then he loses $1. That's $1. Then here for 5, if he 6 in advance, 5, that's $2.50 minus, and that's $2. Okay, so this is the table in which so this is the table that tells you all the possible values. Okay, and so now you just use this table. You take each value of y sub 3, multiply it by the respective probabilities, add up the products, and you get the value of each expected value. Okay, so I'm going to do that quickly on the whiteboard. Okay, and so now you just find the value of each expected value from the whiteboard. So E of y sub 3 is then going to equal, take $1.50 and you multiply it by the probability that y sub 3 is that, which is 5/12. Okay, and so you get that that's equal to, and that's times the probability that y sub 3 equals the 1.5. And so then you multiply those two and you get 1.5. Similarly, use the table to get that E of y sub 4 is equal to 1.58. E of y sub 5 is equal to 1.33. And E of y sub 6 is equal to 0.92. And so those are all the expected values. And so so how many magazines should you order if he wishes to maximize expected profit? You look at the largest expected value, and that's E of y sub 4. So the conclusion is that since the value of y sub 4 is the largest, he should buy 4 magazines in advance to maximize his expected profit. Okay, and so that's the end of 6.2.2. That's the end of 6.2.2. And so for homework, I'm going to assign okay, so for homework, no, not that one. So for homework, you should see the homework screen now, Kishan. So for homework, I'm going to assign homework 7. Second one. Okay, so for homework, I'm going to assign homework 7, and I'm going to assign homework 8, but 6.1.4 homework 8. Okay. So sorry. There we go. Okay, so the homework 7 and homework 8, section 6.1.4. That's the homework. Okay, you're welcome. Wait, hold on 1 second. The homework, right, 6.1.4 and homework 8 and homework 7. Okay, good. Okay, right, a reminder, S2 is this Thursday. And also a reminder, the final is next Monday, right? So the final is on the 16th. So the final is on 8/16/2021. S2 is this Thursday, which is 8/12/2021. Okay. Okay, and so homework 7 and homework 8, section 4 is due next class on Tuesday. Okay, which is 8/10/2021. Okay, so homework 7 and homework 8, section 6.1.4 is due tomorrow. Okay, and test 2 is this Thursday, and final is next Monday. Okay, so I'll see you tomorrow. Okay, have a good day. And I'm going to save the whiteboard. Thanks, Kishan. Okay, bye. You too. See you tomorrow.